Welcome to this deep dive into Kubernetes, exploring how we go from zero to hero in container orchestration. In the past, architectures were monolithic, meaning if one part failed, the whole application failed. Today, we use microservices, which are agile and scalable, but introduce complexity. If we think of shipping, Docker provided the standardized container for software. But we need an orchestrator to manage the cranes, load the ships, and track the entire fleet. This is where Kubernetes comes in. The complexity is highlighted by the saying, managing 5 containers is a script, but managing 5,000 is a nightmare. This is why we need orchestration. Enter Kubernetes, or K8s, often called the operating system of the cloud. It abstracts away the hardware, allowing us to talk to the Kubernetes API, treating many machines as one large programmable computer. A Kubernetes cluster has 2 main parts. The control plane, or the brain, makes global decisions like scheduling. The worker nodes are the muscle, running your applications and workloads. The control plane components include the API server, which is the front desk for all communication. The scheduler decides where pods run. etcd is the memory holding all cluster data, and the controller manager ensures the desired state is maintained. Inside the worker node, the kubelet acts as the agent, talking to the master. Proxy handles network rules, and the container runtime is the engine that actually executes the containers. The smallest deployable unit is the pod. Kubernetes wraps containers in pods, which act as a logical host. Multiple helper containers can share a single pod's resources. Kubernetes uses a declarative approach, similar to a thermostat. Instead of imperatively saying start this server, you declaratively state, I want the temperature to be 72 degrees, and Kubernetes makes it happen using YAML files. Deployments allow you to define your desired state, such as wanting 3 copies of an application. Replica sets ensure that this exact number of pods is always running. Updates are handled via rolling deployment with 0 downtime. Horizontal pod autoscaling automatically adjusts the number of running pods based on CPU or memory usage, scaling your application capacity to match user traffic without manual intervention. Since pods are ephemeral and constantly changing IP addresses, services provide a stable address. A service defines a logical set of pods and acts as a load balancer to access them. Ingress handles external HTTP and HTTPS traffic, acting as a smart router at the edge of the cluster. It directs incoming user traffic to the correct internal service based on defined rules. For data permanence, persistent volumes act like external hard drives. They ensure that data, especially for databases, survives container crashes and restarts, keeping your application stateful. To separate configuration from code, ConfigMaps store non-sensitive data, and secrets store sensitive data like passwords, typically encoded in base 64. Both are injected into pods as variables or files. A major power of Kubernetes is self-healing. If a node dies or a pod crashes, the control plane instantly detects the event, reschedules, or restarts the pod on a healthy node, ensuring continuous availability. The ecosystem tool Helm acts as the package manager for Kubernetes. It simplifies the complexity of YAML manifests, allowing you to package, share, and deploy entire applications with a single command. In summary, Docker creates and runs containers on a single machine, acting as the shipping container. Kubernetes manages and orchestrates containers across a cluster of machines, acting as the port authority with automatic scaling. Kubernetes has established itself as the standard for cloud-native development and is the undisputed foundation of modern DevOps.